Okay, so yeah, I hope we covered optimization properly. Okay, so I suggest all of you to go through this algorithms again, okay, and make a chart like what optimization method we learned so far, what optimization method like will be useful, okay, like slowly coming towards Adam optimizer. How is the path towards this Adam optimizer? Okay. Okay. So yeah. Yeah. So after optimization, I strongly suggest you cover optimization because that will be our second this month test. Okay, March we should have a test. So you should decide when it should be. Okay, next week or next to next week. Hmm? Okay. So then we'll cover the next module, that is regression. Okay, what is regression? So regression. Of course, the aim of this will be to learn about least square regression. Then we'll try to see how to use pseudo inverse for regression. Pseudo inverse, that is Murray-Penrose generalized inverse. You'll see how they come to picture. Then we'll see how you can solve using pseudo inverse a regression problem with multiple variables, multiple independent variables. That is y as a function of suppose x1 and x2. How you can use regression for that. We should see then we should see like how you can use regression, how you can visualize regression as neural networks, how you can visualize regression as neural networks. We will see how you can use multi-layer perceptron for regression, how you can use multi-layer perceptron for regression. Okay, so these will be the part of this regression. So this is the second most important module in this course. So after this module, we'll slowly go to different methods of PD, OD, and integration differentiation. Only the most important methods, and that will be the end. Okay. So this is the most important one. Fine. So I suggest, like, of course, you have this. You already know. It takes some input and gives you some out. That's the model. That's the model, right? You give some input and that model will utilize all the computations inside a black box and give you some output. So we'll start with a simple example in your class 12th physics, in your class 10th or maybe class 10th physics. So suppose you have a metal beam. Okay. You have a metal beam, fine. What you do is, yes, you connect it with some voltage. You connect it with some voltage. I hope you must have done this experiment. I did this in childhood. What I did in childhood, I hope you must have seen 9-volt batteries. 9-volt batteries, the tiny one. What I did is, this, what you call this, scrub pad, scrubbing to wash utensils. That metal wire. Huh? I took one of that wire. I took it out. Okay. What I did next is I had this 9-volt battery. Okay. I had this 9-volt battery with this thing. Okay. And what I did is simply connected the wires. And here I put that, what do you call that? That scrub pad wire. Okay. The scrub pad wire has very less resistance. Okay. Very less resistance. Okay. Due to that, the voltage like easily will go. And since the wire is very thin, it will look like bulb. It will shine like bulb. Okay. So that's what I did. And it burnt. Okay, it burnt. Okay. So my attempt was like I was fascinated by electric bulbs when I was kid. So then I thought like why not I can make my own electric bulb, okay, and light up my house, okay. So I used this as a scientific curiosity. I was into these kind of things like to get some materials and do some creative work. So this is known as DIY, do it yourself projects, okay. So then I did this project. Then I saw it was burning. Then I thought why it is burning. It is burning mainly because of oxygen content. Okay, since oxygen is there, it is able to oxidize much faster. Okay, oxygen is playing a role in oxidizing it. Okay, so therefore in bulb, like you might have seen in 20-watt bulb late after 15 years, 10 years, you saw the transparent bulb, yellow light bulbs. Okay, those bulbs inside that is vacuum, so therefore it is preventing to oxidize. Then I thought I should do that. Okay, so then what I did, then I came to this medicines, homeopathy, the small glass they used to give that, and then this cork is there inside it. Yes. So I thought like that is the best way to create vacuum. So I inside that cork I put two wires, and then I did this experiment. Now this wire did not get burnt for around 5 seconds. It lit like bulb, and I thought that is my invention there. Okay, because I at least made a bulb with some 3-4 rupees or something. Okay. So anyway, this was just a visualization of like scientific things. So yeah. So therefore, I like maybe it is math or maybe it is physics or maybe it is anything else. I am always into science. There, my curiosity has started, and I don't want that curiosity to stop. Even some age is also crossed. So yeah. Anyway, just recollected that thing in my mind. So this, I think this is plus, this is minus, plus, minus, 2 volts like that. And yeah, why I told you this topic, I will tell you soon, that you have this wire and this is a metal. Okay, so any metal has resistance. Any metal has resistance associated to it, and therefore that burnt. Therefore that burnt. Okay, else if it was full conduction, if like blood does blood flow through our whole body? Does it light up? No, right? So why if current passes through that filament, it lights up? Because it opposes, some part of it opposes the current to flow. And due to that opposition and uh, transition, due to that, that heat is produced and that is brightening to you. Okay. And that's how the light we are seeing it. Okay. So therefore, there is some resistance R for this metal rod. There is some resistance R. And of course, due to this voltage difference, current I. Okay. So by Ohm's law that V equals to IR, isn't it? V equals to IR. That is, voltage is proportional to resistance, and whatever different, like you take voltage 1 divided by R1, it will be same as voltage 2 divided by R2. Okay. You take a different rod, apply different voltages, same rod. The resistance will be the same kind of, but you will get this proportionality constant I. That is like the proportionality constant. Current will be the same. Okay. So now the question is, if you only through experimental results, not theoretical, mind you, experimental. Like you should imagine that I have a setup with a metal rod, wires, and I have a voltage, and I am doing this experiment with resistance and all these things, and I am calculating V by R. I am calculating V by. My aim is to find current. So what I do, I plot V versus R, right? I mm, yes, I plot V versus R, isn't it? Agree? Those are the two parameters we have. Okay. So what you will see in real life experiment, what do you think you will see? In real life experiment, you won't see a state. That's the catch. You won't see. Why you won't see? Because this is V equals to IR is like addition, real ideal situation. It's an ideal situation. So in reality, there are a lot of experimental factors we are not considering. What are the experimental factors? Oxygen is present. Oxidation can occur because you are passing. I think you must have seen. You must have seen heavy voltage wires. You must have seen heavy voltage wires. Okay. So heavy voltage wires. What happens? Like you must have seen this current going out. A sound, humming sound is there. Okay. If you see the humming sound, don't go near that. Don't go near that. Near that gun. Why? Why? If it is producing an humming sound, that means the electric field is so high that if it passes through the wire, it is not only passing through the wire, it is ionizing atmosphere near around it. And due to that ionization, it is converting to sound energy, and therefore you are seeing the humming sound. And if we are conductors, okay? If you go near that, then he will say, why I will talk to air? I will talk to you. Okay. Then he will talk to you. Okay. So therefore, if you are seeing humming sound in wires, don't go near it. Okay. Don't go near it saying what is. Okay. Those are very dangerous things. Okay. So I'm telling you that sometimes electricity can be highly unintuitive. Highly unintuitive. Still unsolved. Okay, anyway. But I am really captivated by electronics, like electronics or maybe electricity. Okay, electromagnetism. I am really fascinated. Of course, I'm not doing much research on that side, but till my BSc, in BSc we have to learn as a major. My major was physics. Okay, so I learn I like electromagnetism a lot, like how electromagnetism works and all these things. Really fascinating. Really fascinating. Anyway, so let us come to this. So when you record in your physics lab, what you will actually see this. What you will actually see is this. Okay. So yeah. Why? Because of external noise. Because of external noise, you won't see all of them lying on a straight line. It will be deviating from the straight line. Okay. So there are a lot of noise. How many noise you will consider? There is environmental noise. Okay, maybe here in this room the humidity is more, or maybe the temperature is high. Okay, or there are many other factors. Okay, maybe the wood you are using, maybe the clamp you are using, so many factors. How many noise factors you will consider? Okay, so therefore what you do is you try to fit the data. Okay, so if you fit it, yes, it will be like a straight line. Okay, if you fit it. Okay, of course there are errors. Of Of course, there are errors. Okay, what errors there are? Like you can see, like this point is deviated from this point. Okay, this point is deviated from this point. So there are tiny errors there. And in this class, we will actually quantify these errors. Our aim would be to find the best fit line for this data set. And how we can find the best fit line now that you have covered optimization. Reduce the error. How, instead of saying reduce the error, you say minimize the error. How you will minimize the error? So now this error function will depend on how many variables? Two variables. Error function. The error function will depend on both voltage and resistance. Okay, because you change voltage and resistance, the data set will change. Okay, and the regression line will also change. Okay, the best fit line. So therefore, if it is a function of two variables and you are minimizing the error, minimize E is a function of VER, EVR. Okay, this is the optimization problem. Okay, if you want to minimize this, which method you want to use? Yes, least square gradient descent, and one most you are forgetting is Sylvester, because that's straightforwardly you can apply to two dimensions. Okay, so using Sylvester criterion, we will verify the minimi. What we will do, we will first what we will find? Yes. First you will find gradient and set it to 0. So you will find the critical points. Find the critical points. Then what you will check? Check whether it is minima or maxima, right? Okay. So using Sylvester criterion, you can check the Hessian matrix determinant and the first derivative to be greater than 0. Okay. And find the minimum point. Okay. Where it will have the minimum point. Okay. Like that, we will find the coefficient, that is this y, suppose y hat. This y hat is w naught plus w1x. Then this procedure will give us what is w naught. It will also give us what is w1. Okay, due to that, you will be able to find the best fit line which minimizes the error. Okay, so can you see the relation between optimization and regression a bit? How optimization can come to picture? Okay, and why we covered optimization at first place? Because now if I would have told you about this Sylvester criterion, it would have been blank a bit. Okay. Anyway, so this is the idea. But actually, if you see, the current is equals to, for each, suppose you have how many observation vi ri, I equals to 1 to n number of observations you have, and this is the data set. This is the data set D. Okay, this is the data set D, VIRI. Okay, and how you compute I? That is, if you find the straight line equation, it will be VI by RI. Of course, this is the regression. This is the fit line. This is the fit line. Fine, this is the fit line. But in real surroundings, you won't see this happening. Why? Because there will be some error. There will be some error. Okay, this is the error. This is the error term. And this error we can never compute. We can never compute. How many errors you can keep? Atmosphere error, wooden clamp error, okay, measurement error. The length you are saying 3.1, is it actually 3.1? You can never find the length of anything accurately, and that's how fractal come to picture. Okay, can never find 3.1 accurately. Okay, there will be 10 to the power 6 error. Okay, in order to save the 10 to the power 6 error, if you do, you again will get 4. You can never find. You, whatever you are doing in real world scenario now, even using a scale line, you are actually considering the loss due to the pen nib. Okay, therefore that's the idea. Okay, anyway, so why I am saying this? Why I am saying this? The idea is due to this error. Due to this error. Okay, so how many equations you will have? Number of equations will be n, because you have n such data sets. And how many number of unknowns you have? Number of, think. Okay, this I should say, for each observation the error will be different. Okay, how many such things you have to take care? Try to think of this. And due to that, due to this, if I told you in computational science class, if number of equations, if number of unknowns is more than number of equation, it is not solvable. Okay, you will exactly find in this case. You will exactly find in this case. Okay, so you'll see that the number of unknowns will be greater than the number of knowns, and due to this, like you can't solve this. Okay, you can't solve this. Okay. So therefore, solving for this EI is tricky. So you have to respect that error is there, but we don't need to solve the error. You understood the idea, right? You error is there, but solve. Okay, fine. So yeah. So what you have seen regression? What is regression actually? So regression is a technique used to develop models, okay, from data. Okay. Okay. So what regression helps us to do? Regression helps us to build models, okay, from data. Okay. So what regression actually does? Regression will estimate the values of the dependent variable. Okay. You can see y is a function. Y, you have data set xi yi. This is your data set. This is your data set D. Okay. And what you do, y, you will have the data information about xi's. Okay. Those are the independent variables. Xi will be the independent variables and yi are the dependent variables. Okay. Your job is to find out if, based on this set of data sets like xi, yi, if I give you some new data x star, your job is to predict y at that x star. Okay, and that's what exactly regression will do. If you have built a model, okay, which can give you this, which can fit your data, then you just put x star, which is the independent variable, on that regression line. Okay, and that will give you the y. Okay, the estimation. Okay, so therefore regression estimates the dependent variable based on the given independent variable. So regression is also a basis of machine learning. Okay, it's a part of machine learning algorithms. That is, you are learning from data. Actually, regression is also doing the same. If you have set of data, regression is learning from the data and how to fit the data. If you have another data set, regression will learn from that data as well and find a different regression line as well. Okay, so therefore, depending on the data, it is changing. So it is learning from the data. And learning from data means, yeah, it's a machine learning algorithm. What kind of machine learning algorithm it is? Yes, it is supervised machine learning algorithm. I think you must have covered in other classes, unsupervised, supervised. We will also cover in a basic way, okay, just very basic way. But after this, okay, after regression, or towards how you can visualize regression as neural networks. That time I will give you some basics of ML and neural networks, just, and we'll see. Okay, so yeah, fine. So therefore, this is the estimation. This is the estimation or prediction. So therefore, you will see that sometimes you will say, what is the estimator? Estimator. Okay. And if you have in machine learning jargon, like this guy, now I have said that xi, yi, independent, dependent. Now, if I have xi, yi, in terms of machine learning jargon, you can say this, that this yi is nothing but the response variable in ML literature, response variable. And this guy, xi, is known as the regression. The regression, okay, or also known as sometimes the feature. Okay, so this is just the terminology, and what this D is referred to as training data. Training data set. Okay, so yeah, we are learning from the data that is being given to us. Fine. So if you have a mechanistic model, if you already have a mechanistic model, that means if y is a function of x is already known, that means if you have given x, you already know what is y, then there is no training necessary. If you have a mechanistic model, this is a mechanistic model. If you have a mechanistic model where you already know what is x, what is y, and how y is depending on x, then you don't need any training. You already know how y is changing with respect to x. So training is not necessary. And that's where regression never you will see in those cases. Okay, regression comes when you don't know the idea of how, like you have these data sets and how they vary with respect to independent variables. To know that, you fit a line, you do regression analysis. Fine. So problem occurs when we don't have this. Problem occurs when we don't have this guy, mechanistic mode, and therefore we come to regression. Fine. So if we have a data set, yeah, if you have a data set, suppose if you have a data set, so this is something like a bit insider to regression. Okay, this you will see a bit towards statistics. Okay, but we will not go deep into it. If you have a data set, say tau or t, okay, and it has a linear kind of fit, okay, then we might think of a linear relationship. That is how it should look like theta naught plus theta 1x plus the error term. If you are considering experimental data, there will be some error term. Okay, usually this error term people use it in regression to model the real life scenario. So, like I told you, voltage and that resistance example, there is some error associated. Okay. Similarly, here theta naught plus theta 1x. If you want to show it like a real world variable, you put some noise, and that noise is usually zero mean error. Okay, zero mean error kind of thing we put from that distribution. Okay, normal distribution. Fine. So, but why I am saying this? And this error, mind you, is independent. This is independent of x. This is independent. Okay, this from the theory. This is from the theory. Okay, but as we saw, you cannot like you are adding it, but if it is a real world experiment, you cannot compute this error. If you cannot compute this, you cannot also compute theta naught and theta 1 also. Okay, you cannot compute theta naught and theta 1 also. Okay, if you are not able to compute errors. Okay, so what we can do, we cannot find theta naught and theta 1, but we can find something like a regression fit, a simple linear regression fit. There is a subtle change in notation. Okay, here y naught is like w naught plus w1x. Okay, but addition is residual e. This is known as the residual. Okay, e is not equal to this e, and this is not equal to the error, that noise you are seeing. Okay, but the idea is you cannot compute this, rather you can compute this. Okay, you can visualize that if you use linear fit, that is w naught plus w1x, which we saw in the previous slide, there will be some residuals. Okay, but that you cannot say that is the error, same error as experimental. Okay, we are just modeling it. Okay, so this is just a subtle difference I wanted you to know, because usually no one tells much about this. No one tells much about this error or the noise coming from the real source, real experiments. But usually you will see everywhere this residual. Okay. So you can, but this computation of all this, the first one is more oriented towards statistics. We will not discuss that here. Okay. But it is open to you. You can go and explore the difference between the two. In real life experiments, you compute noise error epsilon. For that, what we do a minor change. That is, you do a simple linear, that is W0 plus W1x plus E. E is the residual. You can compute it. W0 plus W1x is the fit line. What are the residuals compared to the original data set? Okay. If data set is here, your regression fit line is here. What is the residual? The distance between this point and this line. Okay. That is the residual E. So this is the idea. Okay. So actually, yeah, we can recapitulate. So now I gave you what I did in this past two slides. I gave you a fact that considering real life problems, there is a noise associated. So you should not think that if given a set of data, we are just plotting it. You are neglecting that error. You are just neglecting the noise. But I am telling you that noise is there. So don't take that for granted. Okay. Anyway, so what we have learned so far, we told that if it is, now we'll see simple linear regression. That will be first aspect here, simple linear regression. What we will do is, we saw y is equals to y hat plus the residual e. Okay. So what is y hat? Y hat is the least square approximation. You can say approximation or the estimation of y. Fine. So therefore, since it is estimating, this is the least square approximation and it is estimating, it is also referred to as something known as estimation function. It is also referred to as estimation function. Fine. So this y hat that we saw usually is w0 plus w1x. So if you see this w0 and w1x, these are the coefficients, okay, of your regression line. And in machine learning jargon, you can say these are w0 and w1 are weights. So therefore, that's the motivation to take w as the variable. Okay. So we usually in math books, you can see y hat equals to a plus bx. You find a, you find b. But if you are in machine learning jargon or neural networks, you will say w0 plus w1x, w0, w1 are the weights. Okay, fine. Okay. So this is our regression model. Usually in machine learning, it is said to be as bias, the constant one, and this is referred to as the weight. Okay, so these are some terminologies. Okay, fine. So if you go back to this, one more important step I forgot to tell you here, as compared to this 1 and 2 model, is W0 and W1 are the least square estimates of theta naught and theta 1. Okay. W0 and W1 are the least square estimates of theta naught and theta 1. Fine. Okay. So this you cannot compute. I'd already told you. Since you cannot compute, you have to estimate it. How you estimate it? Using simple linear regression fit and least squares. You come across this y equals to w0 plus w1x plus e, the residual. Okay. So therefore, how theta naught will differ from this w0. How theta 1 will differ from this w1. So w0 and w1 are the least square estimates of theta naught theta. Fine. Now, how to find? Now the main question is how to find the best w0, w1. How to find the best w0? Any ideas? Any thoughts? We are in a very simple linear regression fashion. It should be very simple to you. You already learned it. How you can find w0 and w1? Get ready with your notebook and pen. You have to do some calculations. Okay, and you have to tell it. You have to tell me. Okay. Since you already done optimization before, you should be able to do it. Okay. How to find the best w0 and w1? How? At least to use something there. Oh, I told you. I told you here told you here. Here, right? That you can see these blue points are actually the data set given to you, and the line is actually the linear fit regression line. Okay, so this line is W0 plus W1x, isn't it? So therefore, if you change W0 and W1, the line will shift. The line will shift. Okay, and where it starts from? It can, if W0 is 0, it will start from the origin. If W0 is somewhat non-zero, that's the intercept. It will start with somewhere here. Okay, so therefore, depending on W0 and W1, the regression line will change its orientation and position. Okay, in a way, so it will be like this. If you do the W0 W1 optimization, the data set will be there. Your line will be doing like this with the how to fit the line. Okay, the moment it says that error is less, it will fit. Oh, I understand why I'm moving my hand, right? That's the line. Okay, got the idea. So therefore, we have to compute all these distances. We have to compute all these distances. That's how, if we minimize the distance, then we are trying the regression line to be very close to the set of data. Agree? Mr. Samuel, let's see here. You want to work? Let's see. There. So did you understand this? Or what? Yes or no? So how to find the best W0 W1? Or the question is how to minimize the loss, how to minimize the error. How? So for that, I told you those set errors, those errors we are denoting by E, those depend on W0 and W1, isn't it? Yes. So we have to minimize that E, W0, W1. How we can minimize this? This you can write it as the average 1 by n summation of I equals to 1 to n Li. Each Li are the loss function. Okay, loss functions. Okay, what is Li? Li is nothing but Ei squared. Taking the distance only, because if you take above the line, it will be positive. If you take below the line, it will be negative. High chances they add, cancel out. Your error can come to 0 even if you are not close. Therefore, we are taking the squared of those sum. Okay, you got that. So Ei, okay, Ei, yeah. So can we write E? Can we write E now? So E of W0 W1 is equal to 1 over n. What is each Li? Each Li, what is for the data set Y1? The point Y1. Y1 is the point data set given to you minus the regression, that is W0 W1x. That is W0 minus W1 at x. At x1 you have Y1. So is this correct? Squared. Similarly, you have to do that for n number of data sets, n number of data points. So you have Yn minus W0 minus W1 xn squared. Is it okay? Okay. Now this is E W0 W1. You have to optimize this. You have to optimize this. So what you have to do? You have to take the gradient. Yes. So yeah, we have to set grad E equal to 0. So what you will do? Dou E by dou equal to 0 and dou W1 equal to 0. Can we do that? If you do that, what you get? So I suggest you do this calculation, because otherwise you might feel that through this solving, you will see that a beautiful formula comes up. Very special formula comes up. Okay. If you don't do it, you will not understand how this formula comes up. It will always be like a hidden truth to you. Okay. Can you do this? What is dou E by dou naught? W naught. Nothing. You take the everything as a square. So when you solve it, x square, 2 times x comes. So it will be 2 by n times, I have taken the 2 common. What I will have? You have to differentiate with this one with respect to w naught. What you will get? What you will get? Nothing but a -1. In every case, you have minus w naught. So you will have a -1. Minus, so therefore, and you will have this linear terms. Okay. Is it okay? Fine. Now, how we can write this in compact form, like a summation? -2 by n summation yi minus w naught minus w1 xi I equals to 1 to n. Okay. Any other way we can write this? Any other way? Take the summation of each of these terms. Take the summation of each of these terms. What you are getting? -2 by n summation yi. What should it be? -2 by n summation w naught again and again. That is n times w naught. Okay. Minus of minus is plus. Sorry, minus of minus is plus also here. Minus of minus plus. What you have? 2 by n w1 is constant. I took it outside. Summation of xi. I equal to 1 to n. What this guy gives you? -2. This is mean of y. Summation of yi by n. It's the mean of y. That I am saying y bar. Okay. Plus n cancels 2 w naught. Plus 2 w1. This is x bar. So what you are getting? 2 times w naught plus w1 x bar minus y bar. Isn't it? Agree? Do you agree? What is dou e by dou w1? Anyone? Two times of oh, wait. This is this one. Okay, so again 2 will come outside. Okay, 2 by n. Fine. Now what you will have? You differentiate with respect to w1. So minus x1 will come. Minus x1 will come for this guy. Minus x1 times y1 minus x1 times y1 minus w0 w1 x1, right? Is it okay? Similarly, plus 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 so on till minus xn. Is it minus xn times yn minus w0 minus w1 xn? Is it correct? Okay, right? Is it okay? Any mistake? Any mistakes? Check. If I am writing, you have to check. I think is correct. So what we will get? -2 by n can be write in a compact notation using summation I equals to 1 to n. How we can write this? xi yi minus w0 minus w1 xi. Can we simplify this much further? What do you think? So what we will have? -2 by n summation xi yi, right? Then minus w0 is a constant. Take it outside. W0 summation xi. Okay. Minus w1 is again a constant, but is multiplied by xi. So summation xi squared. All places I equals to 1 to n. Is it okay? Okay, right? So can we even further simplify? Can we further simplify? So you are taking xi, yi and then dividing it by n. So it is like a mean of xy. It is like a mean of xy. So we can write this as minus 2 xy bar. It is like xy bar, minus 2 xy bar, then minus, sorry, you should tell that there are some mistakes. Missing the bracket, right? Okay, then plus 2 w naught x bar, right? Plus 2 w1 x squared bar. Is it correct? Or there is a mistake? Is there any mistake? Are you sure about this plus w1 x1 x square bar? Plus should be there. Plus 2 w1 x bar x square bar, or minus should be there. Any minus mistake? Check. Huh? There minus will be there. Where we have done the mistake? So where is the mistake? I think it is correct. I think it is correct. Correct. Correct, right? I think it's correct. So now what we should do? Now we should set this equal to 0, set this equal to 0, set this equal to 0. What you get from this? What you get from this? Dou E by dou W not equal to 0, dou E by dou W1 equal to 0. What you get? From this, what you get? Hmm? From this, you get W naught plus W1 x bar equals to y bar. From this, what you get? 2 all will be cancelled. Xy bar is equals to W1 x squared bar. Okay. Can we use both of them to find something? Can you use both of them to find something? Do we have everything? What is our aim? Yeah, our aim is to find W naught and W1. So you can find what is W naught here. W naught is nothing but y bar minus W1 x bar. What is W1? So what you do? Put the value of W naught here. So xy bar equals to W naught. That is y bar minus W1 x bar, right? Into x bar, right? So what is there? Okay. Fine. So what is W1? So W1 is equal to, very careful, very careful. What is, what is? You tell. Very important thing which many of you might do the mistake, and very subtle also. Okay, very subtle also. Carefully see how I am writing this to this. Okay, W1, I have to write everything in terms of W1. So xy whole bar minus x bar into y bar. Two things are different. Divided by, what should be there? Hmm? Hmm. Till x bar squared minus x bar whole square. So you know now that this is the value of W1. Can you find, given is, now imagine you are given a set of data, xi, yi. Oh. Okay, but now don't worry about it. Like we know that we got W0 and W1. So what is W0 and W1? Can you tell me what is W0? Y mean minus x1 x bar W1. And what is W1? Xy whole bar minus x bar y bar divided by x bar whole square minus x bar whole square. Oof. Saved you to Rohit. Should clap easy. Then Rohit saves me with his wire. Anyway, so now we know y cap is W0 plus W1x. Okay. So W0 W1 you can easily compute. How you can easily compute? You can compute W1. How you can compute W1 if you have set of data xi, yi. If you have a set of data xi, yi, can you compute x bar from this data? Yes. Take the mean. Can you compute y bar? Yes. Can you compute xy bar? Yes. Can you compute x squared bar? Yes. So you can compute all of this numerator and denominator to get W1. After you get W1, you can substitute this W1 here into the first equation to get W0. This will give you W0. If you get W0, you get y hat. It's okay. It's okay, right? Okay. So this is the idea. Fine. But still we have not covered one most important aspect, that we have not checked whether this W0 and W1 are actually the minima. Are actually the minima. For that, we have to use the Sylvester criterion. Okay. So I will share the notes, but I'm not doing it. But you can check. What you have to do, you have to check the second derivative, second partial derivative with respect to W0. First variable should be greater than 0. Second one is the determinant of the Hessian should be greater than 0. That is, Hessian is positive definitely. Okay. So what we should get, if you take the Hessian, that the determinant of Hessian should be greater than 0. These two steps you do and confirm that this W0 and W1 actually satisfies both of them. W0, W1 satisfies both of them. Okay. Then only it is a minima, right? Then it is a minima. Else it can be a maxima. It will maximize your error, which you don't want. You want to minimize your error, right? Got the idea, right? This is like, try at home. Okay. Fine. Actually, the function E, which you have just seen, the function E which you have just seen is a convex function, isn't it? It's a convex function. Why it is a convex function? You remember it is just a square. Sum of squares. Sum of square, isn't it? Square is like a parabola. So whatever square you do, it is just like a parabola. And is parabola a convex function? Yes, parabola is a convex function. You just don't take any 2 points, draw the curve or the arc. It lies always above the function. Okay, therefore it's a convex function. And since it's a convex function, it will have a unique minima. It will have a unique minima. That's the property of convex functions. Therefore, this minima you got is a unique minima. This minima you got using optimization is a unique minima. What does it tell you? It tells you that this is the only best fit. Can you understand? This W0 and W1 above is unique. This W0 and W1 is the unique minima. Okay. What does it mean? It means that y cap is equal to W0 plus W1x is the only best fit line, the unique one. So if you have found using this algorithm W0 and W1, there is no other W0 and W1 that can minimize the loss function. This is the only W0 and W1 that can minimize your loss function based on your data set xi, yi. Okay. No other W0, W1 will be able to minimize it. Okay. Fine. Why? Because this loss function you saw is a convex function. It means convex function means it has only unique minima, and the minima you computed is that, so therefore a unique minima, and that's it. Okay. So you can observe a bit of deepness in the regression concept now. Okay. Usually what you do, you get this variable and solve it. Yeah, this is the regression line. But why it is a regression line? Why no other regression line can be written down? Because this is the best fit. The not A. This is A best fit means especially in scientific discipline, you should know that A means there can be more than one, but the means it is only one. It is the best fit line means it is the only one. There cannot be any other line to fit it. Best fit. Okay. So this is the idea. So cool. So we'll see. Okay. We'll see this in Python a bit. See this in Python a bit, I think. Yes. So this is what it is. Like you can see the data set I am having here, X data set and Y data set. Okay. You can see X data set is given here and Y data set all in fractions. Both are data sets. What we are doing here, see, here we are just computing whatever you have computed just right now. X bar, that is X bar is the mean of X, mean of Y, mean of XY, mean of X square. Okay. And we are just computing W1 first as XY bar minus X bar into Y bar divided by R minus X bar into W0, W1 you got. Based on W1, you can compute W0. How you can compute W0? Y bar minus X bar into W1. Okay. So now you have the best fit coefficients. Okay. And what you do, just print W0, W1 and plot it. You can plot it here. X1 times, that is the X data set, Y data set W0 plus W1 X1. Okay. If you do that, I'm plotting it in orange, you will see this. You can see W0 is, I am printing W1, W0 first. W0 is 17 point this, W1 is this coefficient minus 0.2. And you can see the blue points are the data set points, which is given to you by this X and Y data set. Okay. X and Y data set. And the orange line is the best fit line. Orange line is the best fit line. Okay, so you can see, of course there are errors, of course there are errors here, but you can see some data sets it is making out, okay, closely. That's the idea. Maybe, but the idea is simple. Maybe your data set is non-linear. It is behaving in a non-linear fashion, okay? But this is the linear fit line. Of course, you can fit a curve to it, okay, non-linear curve to it. That we will see. That we will see. That's the idea. And yeah, we'll see this next. I hope you're getting the idea, right? Huh? Like I think this must be covered already. Did this relation is also covered? It's covered? Not covered. Not covered. How many of you know? This is a sum of square residual plus sum of square, that total error you're trying to find. Not covered. Okay. Because this is important. If you're learning regression, this is important because then you will say it's something known as R2. R2 is nothing but SSR by SST. Okay. Or you can write it as 1 minus SS residual by SST. And R2 is nothing but the coefficient of determination or the goodness of fit. Okay. If you have, you can also write this R as some SXY by root over of SXX by SYY. Okay. And usually it is in between, R2 is in between 0 and 1. Okay. If it is close to 1, that means your regression line runs close to the data points. If it is close to 0, it means that it fails to capture a lot of data points what you have. Okay. If it is greater than 0, R2 is that. So R2, I will tell you R2, if it is close to 1, good fit. If it is close to 0, missing data points. It is missing the data points. That means it is not able to closely fit your data points there. Okay. Whereas R is here, R2 is the coefficient of determination. Coefficient of determination, or you can say the goodness of it. Whereas R is known as the correlation coefficient, sorry. Correlation coefficient. R is the correlation coefficient. Okay. So R2, is it 0 or close to 0, close to 1? Okay. What is R? Based on R, can you say something? So also depending on R, you can say something more. That is, if R is greater than 0, it is a positive correlation. Positive correlation. Fine. If R is less than 0, then it is a negative correlation. What does it mean, positive and negative correlation? So positive correlation tells you that if X increases, your Y will also increase. Okay, if X increases, Y will also increase. But negative correlation will tell you that if X increases, Y will decrease. So R less than 0 is negative correlation, R greater than 0 is positive correlation. If R value is coming close to 0, no correlation at all. I think you must have seen this in your data analytics, no correlation at all. That means Y. Yeah, that means. Okay, so this is what it is. Okay, what is no correlation means? Xi's and Yi's are kind of dependent, are independent. Sorry, are independent. That means there is no relation between Yi and Xi. You cannot say that you get data and you plot it and you will always find a regression line. Okay, like suppose number of fish in the pond and number of times Hari Shankar eating biryani. Okay, number of times he eating biryani and number of fish in the pond. How they can correlate? Yeah, he's eating biryani and number of fish in the pond. Okay, no correlation at all, right? So therefore, yeah, if he eats fish biryani, there can be correlation. But unless that, there is no correlation. Okay, so you can see sometimes data cannot have correlation. In that case, what is the value of R? Near to zero. Okay. Okay. So high values. So yeah, high values of R2, high values of R2 might indicate a good fit, but yes, you should be careful that it should not indicate overfitting. It should not. Overfitting is bad. Okay, so I think that you might have covered already. Hmm? Okay. So R2 should be close to 1. R2 should be close to 1, but should not be equal to 1. So this is R2 should not be equal to 1. If R2, yeah, R2 equal to 1 is overfitting, but in order to avoid overfitting, it should not be equal to 1. Okay. So yes. And also think, I have this question for you. Will the regression line, you know the regression line, will the regression line pass through X bar, Y bar point? What do you think? Why? This question last semester, no one could answer it. No one could answer. See, it is a very simple regression we are talking about. Simplest regression, linear fit. Y equals to W0 plus W1x. Very simple. So I am asking, this is an interview question. This is an interview question. That they will say, consider set of data points I have given to you. I want a simple linear regression line to be fitted. Okay. You say, yeah, Y equals to W0 plus W1x. Then they will ask, okay, regression line, will it pass through the mean of each of them? There, what should be your answer? If yes, why? I should W0 and W1x pass through your fit line. So this is your assignment. Okay. It will pass through Y bar. Why? Y equals to W0 plus W1x. If you put the formula of W1, if you put the formula of W0, what is in W0? Y bar minus X bar W1. I am telling you indirectly, I am asking you if X bar Y bar passes through the regression line. I am indirectly asking you whether X bar Y bar satisfy this equation line, isn't it? If it passes, if the regression line is like this and it passes through the mean, suppose, then that line, that point should satisfy that equation, that curve. Okay, your assignment is that. Okay, will regression line pass through X bar Y bar? So please keep this in attention. We are learning a small part, we are learning it in a very detail. So we are learning linear regression, but we are learning it in a very detailed way. Okay. So yeah. Maybe we should cover this SST part. It's a good time. Yeah. So are you okay with this? So far, okay. Any doubts? Any doubts? So okay. So this is all the part I just covered before deriving all this. Shall we derive this? Or okay? Shall we derive this one? Or is it okay? Like now I told you the see my plan was to derive this SST, SSR, SSRES based on YI bar and all those things. Okay. And then tell you that yes, after you take the division of SSR and SST, it is R2. But how SSR looks like? What is SSR? Can you tell me? Tell me the formula. SSR equal to SSR equal to it's the sum of square of residuals. Okay, sum of square of residuals mean you straight line, the regression line, and there is an actual point, the difference between them, and you take the square. That is the residual, right? How you can write it mathematically, and you sum it up over all the points. So you have to write the first summation I equals to 1 to n for each point. Yi cap minus yi squared. Yi cap means yes, it's the regression line at that point. You cannot take the line and ask. You have to evaluate at that xi. Y cap, what is yi cap? Yi cap is nothing but y cap evaluated at xi. Shabna is okay. Then what is SS res? I think I made a mistake. SSR is some, sorry, this is SS res, is it? This is residual, right? Why are not? What is SSR? Yi minus yi cap minus y bar. Means the predicted, means the regression line point and the mean of y bar, and then you take the square and sum it. Yes, that is what is R? Yes, yes. Sum of square of regression. Sorry. So this is the tricky part. SS capital R for regression. Okay. Summation I equals to 1 to n yi cap, the predicted one, minus from the mean. It's from the mean y bar squared. Okay. Fine. What is SST? Don't tell social studies. Yes, what is SST? Again? That is. So yeah, it's the total only. T stands for total. SST. SS means sum of square. T means total. But there should be a formula for it. II minus. So you know this. Yi minus y bar whole square. Yeah, I think I wanted to cover this only. Actually, I wanted to cover how this equation came up. Like T equal to SSR plus SS res. SSR is sum of square regression. SS res means sum of square residual. And SST is the sum of square total. Okay. And R2 is the coefficient of determination, that is sum of SSR by SST. Okay. Huh? So this is equal to 1 minus SS res by SST. That is sum of square residual by sum of square total. 1 minus that. And you can see if R2 is equal to 1, if R2 is equal to 1, straightforwardly, what does it mean? Sum of residual is equal to 0. Sum of residual is equal to 0. If sum of residual is equal to 0, what does it say? It is fitting all the lines properly. Okay, that means like it is indicating kind of overfitting. Okay, that's the idea. And R is Sxy by root over Sxx into root over Syy. What is Sxy? What is Sxy? Actually, from this formula itself, from this equation 1, you can actually derive R. Come, that is unsafe. Come. Justice should be there. Okay, so the idea is so see, yeah, it will be in my notes. It will be in my notes. But the idea is simple, that if you from the equation number 1, SST equal to SSR plus SSRS, you can actually derive SXY. You can actually derive this cross correlation coefficient. Correlation coefficient formula actually from equation 1 itself. So if you know how to derive equation 1, you can actually derive equation R. Okay. Now what is SXY? You tell me. What is SXY? SXY and SXX, SYY.